The expectation-maximization, or EM, algorithm is used when some data is missing or hidden. Its goal is to estimate the most likely parameters of a statistical model. EM does this through two repeating stages, the E step, which estimates hidden information, and the M step, which updates the model parameters. These steps repeat until the results stop changing significantly. This is called convergence. In simple terms, EM uses what we currently know to estimate what we do not know, then improves the model using those estimates. The core idea of EM is a repeating feedback loop. First, the E step estimates missing or hidden information using the current model. Then, the M step updates the model parameters using those estimates. The improved parameters are then used in another E step. This continues until the model converges. Each iteration helps the model better explain the observed data. Think of it as repeatedly making an educated estimate, updating the model, and then making a better estimate based on what was learned. EM is useful when important information is missing or hidden. A common example is clustering, where we have data points but do not know which group each point belongs to. EM is also used in Gaussian mixture models, missing data problems, hidden state models, and machine learning. In finance, it can help identify hidden market regimes, such as calm and volatile periods. The common pattern is simple: we can observe some information, another part is hidden, and we need to estimate model parameters despite that missing information. In EM, we usually describe the problem using three symbols. X represents the data we can observe. Z represents the hidden or latent information. Theta represents the model parameters we want to estimate. The challenge is that estimating theta would be easier if we knew Z, while estimating Z would be easier if we already knew theta. EM solves this circular problem by alternating between them. The E step estimates Z using the current theta, and the M step improves theta using those estimates. The E step stands for expectation. During this stage, the current model parameters are treated as fixed. The algorithm then estimates the hidden information based on the observed data. In a clustering problem, this might mean calculating the probability that each observation belongs to each group. Instead of forcing a single answer, EM can work with probabilities. The main question of the E step is, based on the model we currently have, what should we expect the hidden information to look like? The M step stands for maximization. After the E step estimates the hidden information, the M step uses those estimates to improve the model parameters. It chooses the parameter values that maximize the expected likelihood of the data. In a clustering example, probabilities from the E step can be used as weights to calculate new cluster averages. Those updated parameters are then passed back into the next E step. So the E step estimates hidden information, while the M step improves the model itself. The full EM workflow has four basic stages. First, initialize the model with starting parameter values. Second, perform the E step to estimate hidden information. Third, perform the M step to update the parameters. Fourth, check for convergence. If the model is still changing significantly, repeat the E step and M step. If the changes are very small, stop. EM can sometimes converge to a local optimum, so analysts may run the algorithm several times using different starting values. Remember, initialize, expect, maximize, and repeat. This graph shows how EM improves the model over time. The horizontal axis represents iterations, while the vertical axis represents log likelihood. As EM repeats the E step and M step, the likelihood generally increases or stays the same. Early iterations may produce large improvements, while later improvements become smaller. Eventually, the curve flattens and the algorithm converges. However, convergence does not guarantee the absolute best solution. EM may stop at a local maximum, which is why different starting values can sometimes produce different results. Think of EM like solving a puzzle with missing pieces. During the E step, you look at the pieces you already have and estimate what the missing pieces probably look like. During the M step, you adjust your understanding of the overall picture so everything fits together better. Then you estimate the missing pieces again using the improved picture. This process continues until the puzzle becomes consistent. EM works in a similar way: estimate what is hidden, improve the model, and repeat until the solution stabilizes. The expectation-maximization algorithm is used for models with missing or hidden information. The E step estimates the hidden information using the current model. The M step updates the parameters to better explain the data. These two stages repeat until the model converges. EM is widely used in clustering, Gaussian mixture models, statistics, finance, and machine learning. The easiest way to remember it is this: estimate the hidden information, improve the parameters, and repeat. Expectation. Maximization. Repeat.